Thanks again, the speaker.
Okay, thank you.
And we are going to proceed to the next speaker is Jian Yao from UCAR. He will present our recent progress on sensing thermospheric density using Cosmic-2 satellites.
So where is the, oh, yeah, where is the slide? Okay. Yeah, hello. It's a lot of pressure after two invited talks. So yeah, and I'm Jian Yao, and this is I think the slide is a little bit incorrect, but anyway, so this is a work under me, and also I've done the work collaborate with Jian Peter Weiss, and so I think the author name should include Jian. So, but anyway, so here is the I will talk about the recent progress on sensing thermospheric density using Cosmic-2 satellites, and yeah. Okay, so here is the outline of my presentation. First, I will talk about why do we need to study the thermospheric density, and then how to sense the thermospheric density using LEO precise orbits. And then I will compare my result and with the model daily average result, and also the high resolution result. And then I will talk about some products we've generated, and some future work. Yeah. Yeah. So why do we want to sense thermospheric density? The atmospheric density is already very low at the LEO satellite altitude. However, its forces can still accumulate to impact the satellite orbit significantly. So here is a illustration of the drag force on the satellite. You know, if we have no drag force, then the satellite orbit will repeat every cycle. But if there's a drag force, then the satellite orbit would, you know, the satellite would approach the Earth little by little. And so with the faster growing LEO satellite constellations, we really want to monitor and predict the thermospheric density at the various altitudes and locations in order to avoid satellite-to-satellite collisions, and that's already happening, and also satellite-to-debris collisions, right? So, and also the thermospheric density has increased dramatically over the past years because of the solar cycles. So yeah, that's the reason. And here is the basic technique of sensing the thermospheric density. So if we use the POD software such as Bernice, we can estimate the total non-gravitational force. And then for the total non-gravitational force, it's mainly composed of drag force and the solar radiation pressure force. Okay, and so for the solar radiation, yeah, well, that's great. Okay, so for solar radiation pressure force, sometimes it's against the satellite velocity. So suppose the satellite velocity is moving like this, okay, going clockwise, and then the solar radiation pressure force is against the satellite motion, and sometimes it's accelerating the satellite motion, right? So if it is here, then it is accelerating the satellite. So if we have like daily average, then for each day, the satellite rotates around the Earth for roughly like 15 cycles, and the solar radiation pressure force, the impact on the satellite velocity is essentially the net impact is almost zero, right? So that's and oh, okay. And so for the air drag force, you know, it is related to the thermospheric density, and also related to the effective satellite area, and also the drag coefficient, okay, and also the satellite velocity squared, okay. And so if we do the daily average analysis, basically we average down the solar radiation pressure force to almost zero. And then we can look at the around track non-gravitational acceleration and compare it with the thermospheric density. You can see that they have very good pattern match. Of course, I shifted the curves for better visualization, but you can see that they all of them have a peak around 59175 that day. And so you know, and also for this satellite, it is at a much higher altitude, and then certainly the acceleration is very small because the thermospheric density is much smaller there. But we can still rarely see a small peak around this region, right? So yeah. And then we look at like whether we can do a little bit higher resolution, right? So we can do the POD at a resolution of every 5 minutes. And so certainly for higher resolution, the one important thing is that we need to model the solar radiation pressure force very carefully. And certainly that we need to have the check angle and the trim angle. And so that's provided every 10 seconds. And so this is I use Cosmic-2 satellite as the example here. And yeah, so here is the non-gravitational acceleration estimated by Bernice GNSS software, and we have the total acceleration, okay, and we also have the modeled SRP acceleration, and certainly the zero is the when the satellite is in the Earth's shadow, and so then we can do the subtraction to get the LJAG acceleration, right? And then we also have used we can use the NRL MCS model to get the around track jag acceleration and compare our calculated jag acceleration with the model jag acceleration, and they have some good match. Of course, it's not exactly the same, and you can see that the shape is not exactly the same. It's just the peak they sort of match each other. And then move forward, we can calculate the high resolution thermospheric density. So this is the product that we have. And so thermospheric density and the density value here, the unit, latitude, longitude, and height. Okay, so certainly the height is roughly 530 kilometers. That's the Cosmic-2 satellite height and altitude, right? So we have those file, and then we can compare our result with the NRL MCS model. Certainly, you know, they are not exactly the same, and there's some distortion, and yeah. But then what I did is that I checked the satellite layout and calculate those areas very carefully, and also the sunlight reflectivity very carefully, and then we get the updated estimation shown by the black curve. And certainly the peak is not as sharp as before, and also the bottom, you know, sometimes is below zero, but that's another issue, and I will talk about it later. But so this is some improvement here by correcting the satellite surface area and the sunlight reflectivity. And also we can apply this this analysis toward geomagnetic storms. So for here, I don't know why it doesn't display very well here, but if the y-axis is still a long track non-gravitational acceleration, and it has this curve pattern. And this is the thermospheric density from the NRL MCS model. And again, we can see some very good pattern match. And if we look at the thermospheric density sensed by Cosmic-2 satellite #1 on January 20th, 2022, so this is still a peaceful day, okay? And you can see that our latest estimation against the NRL MCS model, and they have some good match, and of course it's not exactly the same, but you know, that's that result. And then we look at the date that we have very sharp thermospheric density, right? So that's a geomagnetic storm on February 3rd to February 5th, 2022. Okay. And then you let's look at those those 2 days, February 3rd to 4th. And you can see that our estimation is a little bit far away from NRL MC's model. NRL MC's model is essentially the same over the whole 2 days because probably they don't incorporate some, well, their daily resolution is not that high, right? So, and we can see some variation here. And so, of course, someone may ask me, why we have some negative number and this, and then recently I revised the algorithm a little bit more, and so, yeah, but that slide is not shown here. Like what I said, the slide was not updated, but then another recent change will fix the zero, below zero issue, and the curve also changed a little bit because I double checked some signs in the calculation, and after consulting with the Bernice team, and yeah. But other than that, so for the yeah, what's that? Yeah. Okay, and looking forward, I will continue improving the performance of thermospheric density sensing, and by checking all the details of my computation. And I'm also interested in generating the products for space weather community routinely, and the more satellite constellations, the better. Certainly, we use Cosmic-2 as an example to show that it works. But if we have more satellites at different altitudes, then the sensing result will be better, and we can essentially form a global map of thermospheric density. That will be great. And I also look forward to collaborations on applications of these products, such as satellite trajectory prediction. That's very important, and also the geomagnetic storm studies and some models try to incorporate. If someone is interested in incorporating the real observation of thermospheric density into their model, that will be great. And last, I would like to thank UCA's Cosmic team, especially Jian, Peter Weiss, for the support of the work. And here is my email, and I recently moved to St. Louis University, and yeah, but this work is mainly done at UCA. So yeah, and with that, I would like to thank you for the presentation. Oh, what? Yeah. Okay, and so that's that.
We have time for a couple of questions, if any.
This is a very nice talk, by the way. Thank you. Has there been any discussion of making this a data product?
Mm-hmm. So I don't know where it very much depends on Irfan and the sweepsy, right? So yeah, it's but from my perspective, I can possibly generate those products every day, and it's not that difficult. But on the other hand, the products itself is not perfect, right? So we need to improve the performance.
So one comment, so I think that's, again, that great work. So there are a couple of studies that NOAA has is interested in. One of the work that Jian is presented here, Cosmic-2. NOAA has also funded another work that's looking at data from Starlink. So there is a workshop. I mean, certainly we have an interest in creating a data product from this technique, but there still needs to be some additional work. So before we can actually put this data product into operation, but certainly NOAA is interested in making progress. The question that I have for you is, so you've done some comparison within RLMSys, and you said, yeah, there's certainly differences, and that also could be because in RLMSys is a climatological model. So just from your perspective, what do you need to validate? What type of data is out there that you can use to validate this type of data product?
So I'm thinking that probably we can compare with Eric Sutton's result on using Starlinks, and see if we see, because Starlinks are at similar altitudes, and probably if we see something similar curve patterns, then that can, he is using a different method. So, and then that can be used to verify whether my result is good or not, and or I create more troubles than the problem myself. Yeah.
And perhaps some satellites that equipped by both GPS tracking receiver and, for example, accelerometer, like Grace, Gotcha, something like this, when you have two independent instruments and you can simply apply your technique and cross compare.
So you mean they use different GPS receivers, or?
There is some subset of satellites in the past, they have accelerometer on board.
Right. Oh,
Just
yeah.
like-
That's another way to verify.
Just
Yeah.
apply
you-
the technique for GNSS
Mhm.
observations and cross compare two instruments.
Yes, that's right. So for other satellites, then I need to process the solar radiation pressure again, and that will be something tricky. And we need to. Right now for Cosmic-2, I use the 10 seconds resolution of check angle and trim angle. So, but for other satellites, I need to get those information, and so yeah.
Well, very, very quick.
Yes, one very small point. If you're tracking SRP, are you also tracking lunar and solar gravity? That could explain why you're going negative sometimes.
Oh, well, I think the negative, recently I changed the algorithm a little bit, and then this negative, I mean, like this one is gone, and it's mainly, I think, occasionally we may have negative. It's just because we model the solar radiation pressure, here. If we model it not exactly correctly, then
What I'm
when you
saying
do
is
the
there's
subtraction,
another non-gravitational force.
right, the gravitational force is calculated by Bernice. They use like econ model to fit the POD result they have, and then they get this acceleration, and they already incorporated the gravitational model 100 by 100 and EGM model. So and then the residual acceleration is what I call non-gravitational acceleration. So this is basically, you process the GNSS data, and then you get this, right? And then this is your model. And then if you do the subtraction, sometimes you may get negative number. It could come from here, or more likely maybe from the mismodeling of the solar radiation pressure. And so yeah, it's complicated. But recently, like what I said, I make this curve a little bit, not that negative, and they are shifted a little bit up. So yeah, that's what I can say.
Okay.
Yeah.
Thank the speaker again.
Thank you.
And we proceed to our next speaker, is Irfan Azim.